did two proportions in 10.1. Now we're going to look at comparing two means. Good news, calculator heavy section. Let's go. Here's what we're going to look at. We're going to look at describing the shape of it. Shape, SOCA, right? Shape outliers, center variability. We're going to determine if the conditions are meant to make an inference. We're going to construct and interpret a confidence interval for a difference between two means. Calculate p-value. Perform significance tests. This might be a long one, guys. Buckle in. Alright, so let's say we're just looking at 10-year-old girls and their height. Their height can be modeled with a normal distribution with a mean height of 56.4 inches and a standard deviation of 2.7 inches, right? Then we look at boys, same thing. Normally distributed, the height's 55.7 inches, standard deviation is 3 points. So there's more variety in boys, but they're usually shorter when they're 10. If you don't believe me, go walk down the middle school. So we're going to take an SRS of 12 girls and 8 boys and measure their heights. What do we expect for the shape? Each individually would be normal. We have our mean, we have our standard deviation of the sample, and we pass 10% rule. And this isn't super important, so we all good here. But what can we say about the difference between girls and boys? Here's what that distribution would look like. Okay? It's simulated distribution, so if you did it multiple times, what you'd expect the difference in mean heights to be with your variation. So, if you did the simulation, the difference in heights is the average difference in heights is 1.41 inches. Why do I keep this over here? Okay? Wrong tool. I'm still learning. Still learning how to teach, guys. 10 years into it. Alright. Oh, they did it. Alright. So, here we go. Alright, so the mean is 0.7. Standard deviation, we're going to square them, add them together, square root it. This should look familiar. We did this in chapter 6. Okay? So, the sampling distribution. All I care about is shape right now. Shape, variability, all that good stuff. So the shape in the difference of two means is normal if each distribution is normal. And you can tell that because if both are large, or both populations are normal, or if one is large and the other one is normal, if one has a sample of over 30 and the other one's from a normal population, okay? So there's a lot of ways to tell if the difference is normal. Whoa, what's going on with my hair? The mean, you just subtract the means of your distribution. Wow. Standard deviation, you take the standard deviation of each set. Remember to divide it over the N1 and N2 respectively, because we're looking at the standard deviation of the distribution, not of the population. So make sure you square them, add them together, square root. This is all review from chapter 6, chapter 9. This is from everything combined. 10% rule, still the 10% rule. Make sure you check it for both sets of data. Okay. I'm going to take this girl's place. Look at this. Haha. Alright, let's look at an example. A fast food restaurant uses a filling machine to pour soft drinks. Has a small, medium, large drink settings. According to manufacturer, should be 27 ounces with a standard deviation of 0.8. And medium should be, I'm going to do that, mean, standard deviation. In the medium setting, you should get a mean of 17 ounces and a standard deviation of 0.5. To test a claim, they're going to fill 20 cups with large and 25 cups using medium. They don't have to be the same size sample. And see if the difference is 10. Alright? So let's see, this was normally distributed, normal distribution. Okay, good. All right, let's do this. So what's the shape going to be? Good question. I'm happy y'all asked. Shape's going to be normal because both populations are normal. Yes, easy one. What's the mean going to be? Well, y'all should know you should subtract them. The mean's going to be 27 minus 17, which is 10. Again, we're subtracting the big from the, or the little from the big. Sorry, I'm going through this really quick. Standard deviation. I'm going to take the standard deviation of the 1 divided by 20 because I've divided by my sample size for the sampling distribution. I'm going to take my standard deviation of the other, square it, divide by 25 because that's how large the sample size was for median. Again, they don't have to be the same sample size. Eyes hurt today. And we don't check 10% because because we are not sampling without replacement. Okay? There is replacement. Each drink is a separate entity. It does not depend on the drink before. So we don't even have to check 10%. It's been a long time since we had independent samples. I know. I know. All right, I'm rapid fire. Let's get to the good stuff. Oop, whoa, I didn't interpret. So we found standard deviation. Interpret. The difference in the sample mean typically varies standard deviation from the true mean of blank, right? Plug in whatever you want from that. Typically varies is what standard deviation means from the mean. I'm going to go through this really quick. So again, if we're going to, now we're going to go on to and construct confidence intervals. We're going to do confidence intervals, significance test. Okay? The big two. So we have to check random, 10%, large counts. All the rules are the same as before. They have to be random samples, so that way we know we have good data. 10% has to pass, so that way we don't need replacement, and we can take standard deviation. Large counts has to pass, or it has to be from a normal sample, or the data has to look normal and have no skewness or outliers. Okay, this is, watch chapter 9 to review yourself. Look at this beast. All right, let's start by checking if the conditions are met. So here's our apartments. Amount of monies for 1 bedroom, amount of monies for 2 bedroom, right? First things first. Was it random? Yeah, we randomly selected 10 of each. Yay! Now we have to check 10%. I'm guessing 10 is less than 10% of all 1-bedroom apartments. Just gonna throw it out there. Now, if you have 10 0-bedroom apartments, it's still probably less than 10%. Those studios or whatever they're called. So normal large. Now this one, 10 is less than 30. But when we plot the data, there's no strong skewness and no strong outliers. So yeah, they're both normal sets of data, or approximately normal, so we can proceed. All right, dot plots. Remember this formula? Again, this is review. Confidence interval is your statistic, your mean, plus or minus your critical value, like your 1.96 for 95%, times your standard deviation of the statistic. Ta-da! Oh wait, no, that's not it. 1 second, I want to get, go back. There's a question on that all the time. So if you're ever asked what's the standard error, the standard error is this piece right here. Okay? Ta-da! That's your formula. Conditions are met to find a C confidence interval. Your mean is your x1 minus x2. Your t is still the same as before. Well, it's still, remember we use t because it's more accurate for mean. Meant to be. And we're using our standard deviation formula from before. Square them, add them up, square root them. Okay? Now, to find your degrees of freedom, option 2, you're going to pick the smaller of n1 minus 1. So it's not going to be super accurate. There's actually a big formula for it. We don't have to know how to do it. Option 1 is going to be the calculator this time. Let's go. I'd prefer to use a calculator on these. All right, so let's look at this beast. The Dwayne Wade Tract Preserve in Georgia is an old growth of long-leaf pines and has survived in a relatively undisturbed state for hundreds of years until we came and did this research that we had to cut down to find the trees. I hope that's not true. So how do those trees compare to other forests? To find out, they took samples of trees from the north and the south, 30 from each, found the mean and standard deviation. 5 number summaries down below. There are no outliers, so that's good. They took 30 anyway, so I guess it doesn't matter. First, let's look at him and write a few sentences, or click a few sentences and see what's going on. All right? So the shape is going to be normal. I mean, skew to the right. Yeah, because your means here, you have more data to the right of it. The other one looks slightly skewed left, but it's not very severe. But there's no outliers present in either sample. Okay. The center, north has the center about, well, the median's like 18, but the mean's 23.7. So you just say the center for the north is less than the center for the south, or the mean for the north is less than the mean for the south. And variability, northern is going to be larger because it has a larger IQR, interquartile range. The box is bigger, right? Box is bigger means more spread in your data. This is a review from Chapter 1. If you'd like to learn more, go back and make a video on Chapter 1, because I have not done so yet. Why am I talking like, what is this? It's been a long life. Alright. Let's find a confidence interval. I forgot which word the camera was. Alright, so we're going to state what we're going to do. State, plan, do, conclude. State, plan, yeah. But so we're going to state we're going to do a 9% confidence interval for mean 1 minus mean 2, where mean 1 is the true number or height, true mean DBH of all trees in the southern, and mean 2 is in the north. King of the north. Probably be copywritten by HBO for saying that. Alright, we're going to do a 2-sample t-test because we're taking two samples. Okay. Was it random? Yes. 10%? I'm hoping 30 is less than 10% of all trees, or else that's a sad forest. Is it normal large? 30 is equal to 30. We good on both accounts. Let's go. Please make sure we get used to state and show. Don't just state and show. You know who I'm talking to. Initials are MA. Alright. Ma. Alright. So now we do. They gave us the mean. They gave us standard deviation. We have our sample size. So first I would do is jump on my calculator. Beep, boop, beep. I'm done. We did it. We found the confidence interval by using calculator. Is this acceptable on the AP test? Yes, it is. But please put down your T-strokes. Okay. Well, actually, you can't even just say I used to SAM T int to get it. We did it. If you wanted to do it on longhand, you could. You'd have to use a DF of 29, 30 minus 1. That's smaller of the two. And you'd use your table to find T is 1.699. And you do your mean, so you subtract them, plus or minus your T times your standard deviation. You square them, divide by sample size, square root it. Now that would also give you a same answer. Okay. Please use your calculator. You might be asking, how do I use my calculator? Whoa! Conclude! We are 9% confident that the interval from 3.9 to 17.7 centimeters label captures the true difference in proportions between the DBH in southern trees and in northern trees. Cool. How do you use your Mr. Twilliger? I don't know how to use a calculator. I mean, how can we get a cow through the door? So you're going to go to 2 sample t interval. Okay? We're going to use stats. If you have a list of data like the apartments, you're going to plug in L1 and L2 and use data, and it'll do everything for you. It's magic. Can you imagine? No calculators? It's easy if you try. So we're going to go stats. Plug in our mean, standard deviation, and how big our sample is. Mean, standard deviation, how big sample is. Confidence interval is 0.9. We don't pool our data here, okay? That's for the summer, not for school year. You enter, and look at that. It tells you what the degrees of freedom should have been. It gives you the, yeah, that's it. That's all there is to it, guys. This is your interval. We did it. That's all you have to do for this chapter. Again, if you're using data from lists, you're going to use L1, L2. Just put frequency as just 1. We aren't doing a relative frequency thing here. And the apartment, that was the apartment one out. Sure, now you know. It's going to cost you less money to be in a 1-bedroom apartment. Who knew? Who knew? It's salty today. All this tip is saying is use your calculator. There's a lot of chance to make mistakes if you do this longhand. Please use your calculator. Alright. And if you're wondering where all this is, because you don't know, you hit stat button. You go over to test, and it has all your 2 sample, 1 sample, interval, and significance test, actually. So that's what we're going to do next. Gosh, my hair's puffy today. What's going on? Let's finish this beast. Alright, let's do a significance test. Long video, let's go. Monetize it. Ads. This is brought to you by the sweatshirt. I don't even know who makes it. Alright, so our null hypothesis is going to be mu1 minus mu2, and that's going to be a hypothesized value, what we think. Usually it's going to be we're going to assume they're the same and show that they're different, right? This is just like the proportions from last video or last section. Guess what the conditions are? Exactly the same. That's the confidence interval, okay? They're exactly the same. So I'm not going to spend a lot of time on it. Look at that's me. That's you. That's you when I assign you homework. And your problems aren't real. Sorry. Oh, I'm sorry. Kids are just, Alright, so they want to know what's the mean hours worked, standard deviation, see if it's changed over time. Americans think that they work more now, which actually they do. But if you talk to anyone who's older, they'll be like, oh, kids nowadays don't work at all. But technically, actually, statistically, we work more. But anyway, I digress. So they took a sample size of 764, 975, found that mean in standard deviation. 2014, they took another sample of 1501. So pretty good sample size, actually. So do we have convincing evidence that people work more in 2014 than they did in 1975? State your hypothesis. All right, we're going to check conditions first. I'd rather just do the test right now, but our appropriate hypothesis is going to be, we assume that there's no difference, so we're going to subtract the means and assume there's 0. Our alternative is that they're not equal 0. If I was doing this test, I would have guessed that we worked more, and I would have done it greater than 0. But the question itself is asking, is it different? Okay? So be careful on what you're reading and doing. Yeah, just to know what it is. I wish, maybe we can't. Let's just perform this one. Let's just do it. Is it random? Yeah, they took 2 random samples. 10%? There's more than 1,500 workers in 2014. Or there'd be more than 15,000 workers in 2014, I do believe. Normal large? Yeah, it's large. Yeah. I'm going to use my calculator really quick. Let's just see so I'm going to go stat, test, 2 sample, two sample T test. I'm going to go stats. All right, so you guys can see. I'm going to plug this all in. I'm kind of curious. What fun video watching a man plugging stuff in his calculator. Why did I pause it? You asinine fool, Mr. Twillier. You guys can try this at home too if you got a calculator and see if you get the same answer as I do. And you can tell me I did it wrong in the comments below. Yay, internet. Not equal to pool. No. Calculate. I got P was 1.158 times e to the negative 6. So 0.000115. So, yeah, that means we're going to reject the null. Reject the null hypothesis. We work more now than they did in 1975. Come at me. What can I do it? Can I say okay boomer? No, I don't want to. That's terrible. I'm not even young enough to do that. Broke my hip saying that. All right, so again, standardized test statistic. We still have to find our T. Stat minus parameter over standard deviation, which for this one, it's going to be your difference in means minus 0 over your standard deviation, which we talked about before. And when we do that, again, option 1, use your calculator, okay? Please, 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 please. Oh, good planning. Okay, millennial. All right. So again, we have some evidence that there is a difference between them because the difference was 2.94 in our sample, which is quite large with how big the sample was. When they ask you, what's some evidence? You're just giving the straight stats. Be like, well, this one's bigger than this one. So there's some evidence that's different. Let's see if we did it right. Our T value, we could have done longhand and found the difference in means, minus 0. I got negative 4.88. I put the data in opposite. It actually doesn't matter if I denote it the correct way. So I got 4.88 on the calculator as well. I got p-value to be very small. I used a calculator. I got the exact same thing. And that p-value is minuscule, so we reject the null. There's convincing evidence that people work more now, or in 2014, than they did in 1975. Sorry, I did that really quick. You're just going to be using your calculator, guys. Big thing is make sure you state your T, make sure you state your P, okay? In the do. Okay? It's more important that you can draw a conclusion correctly than do the calculations. I'm not going to do this one, actually. If you want, we're just going to plug that into your calculator and do list 1, list 2 to find it. So I'm calling her video. Look at this guy in his milk. He's so happy. Have a great day, everybody.